Okay, so moving on to the last main concept we're going to see in trigonometry. Uh, you'll notice that everything we've done so far has only been done with right triangles. Okay, so with right triangles, we have at our disposal SOHCAHTOA, or we could use even the Pythagorean theorem if we wanted to. But again, everything we did just involved right triangles. But of course, not all triangles are right triangles. There's other kinds of triangles as well. So we're going to need these new rules called the sine, law, and cosine to help us solve some different information in those. So in a situation like this where we don't have a right angle, different laws are going to be needed, and we'll develop those as we go. Now, one thing you'll notice here, we mentioned this briefly in an earlier lesson on similar triangles. Convention with a triangle, if we have triangle ABC, we'll label the sides across from the angles as a lowercase letter of that angle. So again, across from angle A, we'll have side A. Across from angle B, you'll have side B, and so on and so forth. That's going to come in handy because when we finally do come up with the equations for sine law and cosine law, they're based on this convention. Okay, so some other things to remember for triangles. So some of these will be review here. We know all the angles have to add to 180 degrees. The largest side of the triangle, for in this case side C, is opposite the largest angle. The smallest side is opposite the smallest angle. And the sum of any two side lengths must exceed the third, which if you think about it kind of makes sense. Like if you had a picture like this one right here, here we have one side length 2, one side length 3, and what happens is we can't make a triangle because these two side lengths together don't exceed the third. So keeping that in mind when you're coming up with triangles, that the sum of any two side lengths must exceed the third. Okay, so I'd just like you to watch this right now. Don't worry so much about copying it down. This is going to be used to develop the equation for the sine law, and it can be a little bit tricky algebraically. I just want you to follow along for now. So here we have a typical acute triangle, so there's no right angle in it. And what I'm going to do here is I'm going to drop down this vertical here and create two different right triangles, one being ABD, the other one being ACD. Okay, so I'm going to look at each of these triangles separately. In this one on the left here, triangle ABD, the sine of B is opposite over hypotenuse, which is h over c. Okay, and I'm just going to rearrange the equation to solve for that height, which means it's going to be c times the sine of B. Okay, I'm going to leave that alone for now. Come back to it later. Looking at this other triangle over here, looking at angle C, the sine of C is going to be, again, opposite over hypotenuse, h over b. Okay, rearranging the equation for h again, I get b times the sine of c. Now this looks very exciting right now, and it doesn't get that much more exciting, but what you're going to see here is we have an expression for the height here, an expression for the height here. So what we can do, because both of these are an expression for the height of the triangle, we can let these two be equal to each other. Okay, so with that in mind, what I'm then going to do is just do a little bit of light rearranging. I'm going to divide both sides by side C, and then I'm going to divide both sides by side B. I'm just left with this little expression here that sine of angle B over side B is equal to sine of angle C over side C. Now, in theory, I could repeat this process, drop the height down here from B and do another expression. I could drop the height down from C and do another expression for angles A and B. I'm not going to do that. What this is essentially saying is that the ratio of the sine of an angle to the side across from it is the same for any angle side pair. Okay? And this is what the sine law is. Okay, so we'll come back to that. Now, next thing I want you to take a look at is this one. Again, don't worry too much about writing something down. Just try and follow along. This one's a pretty complicated proof, just to follow through the algebra. And again, it's not like I'm going to ask you to replicate this on a test. I just want you to see that these equations aren't magic. They do come from somewhere. Okay, so again, what I'm doing here is I'm just drawing an acute triangle, triangle ABC, and just like with the last example, I'm dropping down a vertical and creating the height of the triangle right there. So I'm going to look at this first triangle right here, ABD, the one on the left. It's a right triangle, so I'm going to use Pythagorean theorem. So in this, c squared, the hypotenuse, is x squared plus h squared. You'll notice I broke down the base here, a, into two parts, x and y, so it's the bases of the two respective right triangles. So c squared equals h squared plus x squared. Now, with that in mind, if I look at x, because x plus y together give me a, rearranging that, that's going to give me that x is equal to a minus y. I'm going to substitute that into the equation for x. Okay. And then once I get down to here, I'm going to expand this out, simplify it, and I wind up with this long, messy expression, which I'm just going to rearrange slightly, moving the y squared over here. So again, not a very friendly looking expression. I'll come back to this later. So now I'm going to take a look at the other triangle, the other right triangle, triangle ADC. And again, using Pythagorean theorem, b squared is equal to h squared plus y squared. Okay, and if I look at angle C, the cosine of C is the adjacent over hypotenuse, so cos C is y over b. Okay, so what I'm going to do then, I'm going to take this, rearrange for y to get y equals b cos C. Okay, so where this all comes together now, and hopefully you're still with me at this point. I might realize I may have lost some of you along the way. But I'm going to replace the y in this equation with b cos C. And I'm going to use the fact that in this, again being a right triangle, b squared is equal to h squared plus y squared. So in this ugly expression up here where I see h squared plus y squared, I'm just going to replace it with b squared. So doing all that, I get this equation right here. And this is a relationship that exists between the sides and the angles. Again, not in a right this is for a non-right triangle, but you get this equation that's called the cosine law. Now, one thing that's kind of neat here, if you try to use an angle here of 90 degrees, see what happens in your calculator when you do the cosine of 90 degrees. And when you try that, you'll see that it actually gives you 0. So if this were a right triangle, where we're looking at the 90-degree angle here, cosine of 90 is 0, so this whole part of the equation would then be gone, and you'd be left with the Pythagorean theorem, c squared equals a squared plus b squared. So in a right triangle, this is what you have, the Pythagorean theorem. In a non-right triangle, we have the cosine law. So again, the process to derive these is pretty ugly. I'm not going to expect you guys to replicate that on a test or a quiz or anything like that, but again, I just want you to see these equations do come from somewhere, even if it's not from a friendly place. Okay, so to summarize here, we get two equations that we can use now for any triangle. We have the sine law, again, which says that the sine of any angle, the ratio of the sine of any angle to the side across from it is the same for any angle side pair. And we have the cosine law over here. Okay, so when to use each one, where this comes in handy, instead of trying to memorize this, the most important thing to use sine law, again, these are all ratios here, so you just need to use any two of these. Let's just say I wanted to work with this, and let's say this one. In order to be able to solve for something here, I would need a complete angle side pair, so let's just say I had angle A and side A, and one other piece of information here. As long as I had that, I could use the sine law to solve for something. Okay, so as long as I have that, I can solve for something using sine law. If I don't have that, I'd be looking at using the cosine law. So in general, when you look at your triangle, that's what you're trying to look for. Am I going to try to use sine law or cosine law? What you're looking for sine law is those angle side pairs. Okay, so with that in mind, let's just try and look at these different kinds of situations and see what law you want to use. So first off, if you're given one side and two angles, here's a triangle right here. So let's just pick a side that we're going to be given here. Let's say I have this one, and it's going to be 20. And let's say I'm given any two angles. Let's say I've got this one and this one. If I know these two angles, well, the fact that all the three angles in a triangle add up to 180 means I could find out this one. So if I'm given one side and two angles, I'm really actually technically being given all three angles. So ask yourself, do I have an angle side pair? Yes, because I have 20 and I have the angle across from it. Do I have one other piece of information? Yes, I have either of these angles right here. So I could use sine law here to solve for either this side right here or this side right here. So in this situation, I'd want to use the sine law. Okay, so now I'm going to skip the contained, not contained here. I'll come back to that definition in a sec. But let's take a look at the case where there's three sides and no angles. So clearing this off here. If I'm given all three sides, so let's just say I have this side being 20, this side being, I don't know, 18, and this side being 15. So do I have an angle side pair? Not at all, because I have every side, but I don't know any of the angles across from it. So sine law here will not work. I have to use cosine law. And in this case, I can use cosine law to solve for whatever angle I wanted, either this one, or this one. Okay, so in this situation, it's going to be cosine law. Okay, let's look at these last two. So each of these situations you're being given two sides and an angle, and we need to look at the definition of a contained or not contained angle. So let's go back to our example triangle down here. Let's say I'm given two sides. Let's keep this being 20 and this being 18. So if I'm being given the contained angle would be this one right here. Okay, so it's the angle that is between the two given sides. You can think of it as an angle sandwich if you like. So this angle is sandwiched between 20 and 18. So let's say I'm given this one as being, I don't know, let's say it's 42 degrees. This one is the contained angle. So in this situation, ask yourself, do I have a side angle pair to use sine law? And again, I don't. I have this angle, but I don't have this side. I have this side, but not this angle, and ditto here. This side, but not this angle. So I don't have enough information to use sine law here. So again, I would have to use cosine law in this situation. Okay, if I change this up slightly differently, instead of giving you the contained angle, I gave you the not contained angle. So let's say I gave you this one, and I don't know, let's make it 62 degrees. This is not contained, so again, ask yourself, do I have an angle side pair? Sorry, check my writing here. Not contained. And hopefully you can see here you do, because I have the 62 degrees and I have the side across from it, so I have an angle side pair. Do I have another piece of information? Yes, I have this 20. So now with this 20, I can use sine law to solve for that angle right there. So in this situation, I can indeed use sine law. Okay, there's a lot going on there, but again, we got two relatively complicated looking rules there. They look complicated, they're not as complicated to use once we set them up, but you need to know when you can use each situation. Again, to summarize one last time, to use sine law, you need a side angle pair. So again, that's an angle with the side across from it, and at least one other piece of information. Okay, if you don't have that, you're using cosine law. Okay, so that being said, last thing I'll mention here with cosine law, again, going back to the convention where the side being named is across from the angle of the same letter. So again, side A would be across from angle A. You'll notice here the angle there, the side here that's by itself, in this case it's A, is across from the angle that's there, angle A. So if I had a version of this with C squared, it would be cos C over here, the angle across. On my other two sides it'd be A squared plus B squared, and I'd have minus 2AB. Okay, so what's important when you're setting these up is that this side and this angle across from each other, and that your other two sides fill in the other spots in the equation. Okay, now let's actually try and set up an example here. So here's our first one. Let's see what we have here. You'll notice that right off the bat I have two angles in here, so I can find the third one because all three angles have to add to 180 degrees. So 180 minus 23 minus 78. Might be faster than me on this one. Gives me 79 degrees here. Okay, so in this situation now, once we have that, if we want to use sine law, we need an angle side pair. Do we have that? Yes, okay, because we have the side length of 87 with the 79 degrees across from it right here. Okay, we don't have any other angle side pairs, but now we can use this to help us solve. So, sine 79 degrees over 87 is a ratio there between this side and this angle. I want to solve for this side right here, so I'm going to use the angle across from it to set up that ratio. So I'm going to have the sine of 23 degrees over x. Okay, so sine of 79 over 87 is sine of 23 degrees over x. And from here on in, I just have to solve. So it looks complicated, I know, because x in the denominator, but we have ways around that. We can multiply both sides of the equation by x. So if I multiply by x, I'm going to wind up with x times the sine of 79 degrees over 87. And here I'm just going to be left with sine of 23. Okay, I'll have to continue this one in the next video because I'm running out of my time here. So I'll see you in part 2. Okay, cheers.